So good morning, and thank you for the opportunity for presenting here. I'm a student at Rzeszów University of Technology and one of the authors of article called The Effectiveness Analysis of Selected IT Tools for Predictions of COVID-19 Pandemic. And our paper summarizes and presents chosen results of our research. And the purpose of the study was to use different forecasting methods implemented in IT tools and to compare the results obtained for a given data set from the curves of the COVID-19 pandemic in Poland. And the goal was to analyze the correctness and degree of fit of the forecasts obtained using different algorithms and to point out the most effective solutions. Predictions were computed using different models and forecasting methods, such as three types of naive method: simple, seasonal, and incremental; linear regression models, taking into account trends, season, and numbers of performed tests in case of infections; exponential smoothing methods, including Brown's, Holt's, Winters, and ETS models; ARIMA models; and autoregressive models built with neural networks, which are called NNAR. And mentioned methods are implemented in IT tools which were used in our study. Forecast package of R programming language includes functions making use of all of them. Statistica software delivers modules for exponential smoothing and ARIMA models. And another program, Microsoft Excel, delivers forecast worksheets which implements ETS algorithm. And time series used in study were built on the basis of data about the daily numbers of infections, deaths, and performed tests between March 5, 2020 and October 25, 2021 in Poland. And for each wave of pandemic, training and test time series were formed, and training set was used to estimate models and generate forecasts of daily numbers of infections and deaths, and the purpose of test set of 30 observations was to examine generated predictions by calculating ex post forecast error measures. And appropriate functions were created in order to compute those measures. Function calculate training errors was used to calculate the values of errors measures of the fit of the model to training time series. Function calculate ex post errors served as a way to compute the value of expired forecast error measures. And those functions found values of metrics such as, for example, MAE, which stands for mean absolute error, RMSE, which means root mean squared error, and MAPE, which means mean absolute percentage error. And custom functions for selecting the best variants of the models and forecasting methods were also created. As an argument, they accept a list of objects and return an index which contains the most satisfactory one, and that means that characterized by the highest number of the lowest error measures values. And the appropriate functions were used to select the models best fitted to the training data, the models giving the most accurate forecasts, and the forecast class objects containing the most satisfactory predictions. And forecasts were generated with the help of functions from R forecast package. In case of naive methods, we used functions such as naive, which implements simple naive method, S-naive, which implements seasonal naive method, and RWF with parameter drift set to true, which implements incremental naive method. And the slide shows results got for the first wave of infection number time series. And created graphs show generated forecasts with training and test series. Predictions and obtained values of ex post forecast errors measures were saved to a file, and the same was done in the case of other forecasting methods. The TSLM function was used to create linear regression models objects. They allowed to describe the time series as a function of trends, seasonal variables, and other external predictors. And models taking into account different combinations of predictors were considered. For each wave of the pandemic, the models that best fit to the training series of different lengths were pre-selected, and ultimately, from among 10 models initially selected for each wave, the one that allowed to generate the most accurate expired forecast for a horizon of 30 days was chosen. And the left side of the slide shows the results obtained at the successive selection stages for the time series of the number of infections. The chart on the right presents the forecast generated by the model finally selected for the fourth wave, and the model taking into account trend and season predictors turn out to be the best variant in this case. And the slide shows results obtained for forecasting infection numbers with ETS models. Those models were formulated with ETS function, and different variants of models were initially selected using three approaches. First one relied on choosing model with best fit to training time series without values equal to 0 based on error measures. The second approach was to choose model automatically with ETS function for time series without values equal to 0. And the third approach was similar to the second one, only that time series could have values equal to 0. And ultimately, models generating most accurate forecasts for 30 days horizon were chosen as the best. For example, model ETS-AAA was selected for infectious time series of second wave, and results obtained with it are presented on the chart on the right side of the slide. In case of time series for death numbers, models were determined automatically using ETS function. ARIMA models were selected with the helpful function AutoARIMA. It picked appropriate values of models parameters after applying Box-Cox transformation to time series. On top of the slide, model types estimated for each pandemic wave are presented. Charts located under it shows result obtained for data describing the course of third wave. On the left side, there are figures with forecast generated for infection numbers, and on the right, we can see the results of using model for death numbers. Slide presents results obtained for time series of first wave with NNAR models. They were estimated with NNetAR function. It uses feed-forward neural network with one hidden layer, and model is built by feeding network with delayed values of time series. Additional external regressors can be also used. In case of infection time series, we also considered models taking into account daily numbers of tests. Structure of neural network is chosen automatically by function. For example, for time series of first wave infections, estimated model used neural network with 6 neurons in hidden layer, fitted with 11 delayed values and 1 value delayed seasonally. Two modules of statistical software were used in order to obtain forecasts. ARIMA models and their predictions were generated using ARIMA and autocorrelation functions module. Type of the model was first selected with AutoARIMA function in R. Afterwards, appropriate parameters were configured in Statistica and results were obtained. And exponential smoothing and forecasting module was used to get predictions with Holt and multiplicative Winters methods. And the chart on the right side of the slide presents outcomes of applying them to death time series for fourth wave. And predictions were also obtained using forecast worksheets in a Microsoft Excel program. And the left side of the slide presents worksheet creation for infection numbers of first wave. Entry data was time series modified by adding constant 1 and undergoing natural logarithmization. And the right side shows charts with prediction values after bank transformation. I mean subtracting constant 1 and performing exponentation. And upper figure presents training data and obtain forecast for 30 days horizon. Second chart compares predictions with test time series. And comparative analysis of the results was conducted for each examined time series, and this slide shows forecasts obtained with different methods for fourth wave death numbers, and those values are compared with real data, which are marked with red dotted line. We can tell from the figure that predictions the most similar to them were got with ARIMA model in Statistica software. And slide presents charts of error measures values for predictions of third wave death numbers depicted before. Now it can be clearly seen that the lowest values of MAE and RMSE could be obtained with ARIMA model in Statistica software. In the case of MAPE, results were similar for ARIMA models in both Statistica and R, but first one was slightly better, and ultimately ARIMA estimated in Statistica turned out to give the most satisfactory forecasts, and those are presented on chart in bottom right corner along with training and test data. As an example of results analysis conducted for infections time series, we picked to present forecasts generated for second wave, and slide shows the chart comparing predictions obtained with different methods with actual numbers. Figure indicates that the best approach can be using multiplicative Winters method in Statistica software. And charts with forecast error measures confirm that assumption. Winters method is the most accurate predictions for 10 and 20 days horizons. MAPE values for those cases are less than 10%, although they are better approaches for forecasting 30 days horizon. Multiplicative Winters method can be highlighted as the best in general, and figure at bottom right presents predictions obtained with it. And slide shows comparisons of forecasts with training and test time series generated with most accurate methods for every infections time series. In case of first and second wave, the best approach was to use multiplicative Winters method in Statistica, and linear regression model taking into account seasonal variables and the number of daily tests gave the most accurate results for third wave. And finally, multiplicative Winters method implemented in forecast R package was best for fourth wave. And if it comes to dev numbers time series, for first wave, the most satisfactory results were obtained with linear regression model taking into account trend and seasonal variables, and multiplicative Winters method was best for second wave. In case of third and fourth wave, ARIMA models estimated in Statistica software gave the best results. And to summarize research with reference to the time series of the number of infections, in most cases the lowest values of the test error measures were obtained for the multiplicative variant of the Winters method. Most often, the most accurate predictions were possible to obtain using the implementation of this solution in Statistica. And in case of dev numbers, ARIMA models estimated in Statistica turned out to be the best. And our research showed that simple forecasting methods can be used to predict the course of the COVID-19 pandemic, although they can have troubles with more complicated time series patterns. And this summarizes and concludes our research. Thank you for your attention.
Is there any question? Andrew, please.
Hello. I have one question. Whether you consider data for the entire population or a specific country or region, I think that the behavior of some COVID variants may be different in the different areas of the world. They may change in the course of the spreading these variants.
Yes, so we considered only data related to Poland.
Okay. Maybe it will be good way in the future research to take this data, to divide this data for different regions.
Yes, for sure, it's a great idea to do in the future.
Okay, thank you.
Okay,
Thank you.
Janusz Furtak, please ask the question.
Yes, the basis of your work was the source data about the pandemic. I would like to ask you, what is your source of the data? It is a trustworthy data from Health Ministry or from the public sources?
We gathered the data based on the information from the ministry. And we created the data sheets on our own. So data is correct.
Yes, okay. So we should trust this data. Okay, thank you very much.
Thank you.
Okay. Okay. Is there any more question? I have one question. What's the size of the data you are using to learn your model? How many records it was in this data?
So the whole data set consisted of, as I remember, 360 observations, and the number of observations used in estimating the models depended on the type of the model.
Okay, thank you very much for interesting presentation and discussion.